Hello students, I am Sonali and today we are going to do the revision of the chapter Electricity. So let's start today's revision. The first question, write the SI unit of resistivity. The SI unit of resistivity is ohm meter. How do you get this? You have to write the formula of resistance. Resistance is equals to rho, which stands for resistivity, L upon A. Okay, because I want to find out the unit of rho, so I'll keep the rho at one side. Okay, then L upon A will go to the other side. It will become A upon L and R is already there. Now just you have to put the unit of area, meter into meter. Unit of resistance is ohm. I can put ohm over here, and the unit of length is meter. Meter will get cancelled. I will be left with ohm and meter. Okay, so ohm meter is the unit of resistivity. Now name the device that helps to maintain potential difference across a conductor. To maintain a potential difference, the device required is either cell or battery. Okay, now when the cells are connected, more than one cells, when you connect, it becomes battery. Now let's take the next question. Write relationship between heat energy. So heat energy is H. We can also write E also. We can also write E for heat energy or any kind of energy produced in a conductor when a potential difference V is applied. Okay, potential difference V is applied. Okay, it has to be directly proportional, because more the potential difference, more the current will flow, more the current will flow, more the heat is produced. Okay, potential difference V is applied across its terminal and a current flows I through the time t. Okay, so we can also write E is equals to VIT. Now as we know that if more current is flowing, more heat is producing, right? So heat is directly proportional to voltage, heat is directly proportional to current, and if I pass that current for a longer time, then also more heat is produced. So even heat is directly proportional to time. Okay, so H is equals to VIT is the formula for this. State differences between the wire used in the element of electric heater and in a fuse wire. We know that electric heater is used for producing heat so that we can cook food on it. Okay, so we need a wire which have high resistivity, because we don't want light to be produced, we want heat to be produced, right? So a wire with a high resistivity should be used in electric heater, whereas in fuse wire we need a wire with a low melting point and high resistivity. So this is the difference between the wires used in the electric heater and fuse wire. Now the two resistors of 10 ohm and 15 ohm are connected in series. So there are two resistors, they are connected in series, right? 10 ohm as well as 15 ohm. And to a battery, so we have to put a battery over here. The battery is of 6 volt. How can the values of the current passes through them be compared? So because we know that in a series, the current flow, the flow of the current is same. Okay, there is no change in the flow of the current. The amount of the current flowing in series, the amount of current flowing in a circuit where the resistors are arranged in series is same. So the ratio of the current will be 1:1. Okay, in series the same current flows through each resistor, so the ratio of the current is 1:1. Let's come to the next question. A wire of resistance 20 ohm is bent to form a closed square, right? So we have bent a wire in a closed square which has a 20 ohm resistance. What is the resistance across a diagonal of the square? So here you can see in the picture, the wire is arranged in a square, right? We have to find out the resistance across the diagonal. So we have to find, let's draw a diagonal over here. Okay, if I draw a diagonal over here, I can see that my 5 ohm and 5 ohm, they are connected in series. Okay, this is a junction point where the current is going to get divided. Fine. So here, so 5 ohm and 5 ohm, they are connected in series, so I can add them. So if I add them, I will get a 10 ohm over here, right? So I can redraw this, we can redraw this diagram, and if I redraw this diagram, I am getting 10 ohm over here and 10 ohm over here, right? Fine. And what we have to do, we have to find out the resistance across the diagonal. So 10 ohm and 10 ohm, they are now in parallel. Okay, so you are going to add these two and these two, 1 upon 10, 1 upon 10. We know that the equivalent resistor in parallel resistance connection is 1 upon Rp. So I'll be getting 1 upon 10, 1 upon 10, and if I take out the LCM, 10 and 10 is 10. So it is 1 plus 1, which is equals to 2 upon 10. Okay, if 1 upon Rp is 2 upon 10, then Rp will be 10 divided by 2, which is 5 ohm. Simple. Now let's do the next question. An electrical fuse is rated as at 2 ampere. The electrical fuse is rated at 2 ampere. Okay, that is, sorry, what is meant by this statement? Okay, it means the maximum current will flow through it only 2 ampere. So we have to be very careful while putting the equipments that the electric appliances should not make the current flow through that circuit more than 2 ampere. Fuse wire will melt if the current exceeds 2 ampere. If the current flowing through that circuit exceeds 2 ampere, that fuse wire will melt. Okay. Now write relations between the heat energy produced in the conductor when a potential difference V is applied across its terminal and the current I flow through it. This we have already done. Next, these are the 3 marker questions. First one is draw a closed circuit diagram consisting of 0.5 meter long nichrome wire XY, an ammeter, a voltmeter, 4 cells of 1.5 volt each, and a plug key. Okay, so before we go to this question, it is very important that how ammeter and voltmeter are connected in the circuit, right? So here we can see that ammeter and voltmeter are connected. The positive side of the battery is always connected to the positive side of ammeter, right? And the positive side of voltmeter is always connected to the positive side of battery. So both in case of ammeter and voltmeter, you have to be very careful that the positive side of the voltmeter and the positive side of the ammeter is connected to the positive side of the battery, on the same side of the battery. So here is the diagram. We have taken 1.5 meter of nichrome wire over here, right? And it is connected to the battery because we have to take 4 cells of 1.5. So 1.5 volt, there are 4 cells into 4 over here. You can see there are 4 cells, 1, 2, 3, 4 cells. There is a plug connected over here, plug key. Then this is our ammeter. This is the positive side, this is the negative side. If you see, the positive side is the positive side of battery is on this side, is on the left side. Okay, so the positive side of the battery is connected to the positive side of the ammeter, right? Now the voltmeter is always connected in a parallel. So we have taken the voltmeter, it is connected with parallel to the circuit, and the positive side of voltmeter is on the same side of the battery. Okay, so here is a diagram of this particular question. Following graph was plotted between V and I value. So we can see there is a graph plotted between V and I. Okay, so we know the formula of resistance. Resistance is nothing but V upon I. So VI graph, whenever you write VI graph, V will be on y axis, X y-axis and I will be on x-axis, right? We have to find the slope. We know the formula of slope. Slope formula is y2 minus y1 divided by x2 minus x1, or in a simple word it can be y upon x. Okay, now let's find out the value. Here we can find out that we can take the value as here they have taken 1.6 volt and 1.8 current corresponding. So at 1.6 volt the corresponding current, this just you just have to, there is a point given over here, join it with the x-axis, that is 0.6 on the x-axis and 1.6 on y-axis. This is y-axis, this is x-axis. Clear? And we know that the formula of slope is y upon x. You can take 1 upon 6 divided by 0.6, and when you, okay, 16 divided by 6, when you do this you will be getting 2.67 ohm. Fine. So this is the answer for this graph. Now what would be the value of V upon I ratio that we have taken when the potential difference is 0.8 volt, 1.2 volt and 1.6 volt respectively? What conclusion would you draw from these values? What can we draw from these values? That if the temperature and the other physical quantities are same, then we can say that voltage difference is directly proportional, or the flow of the current is directly proportional to the voltage difference across the battery. So this is following ohmic law, or Ohm law, sorry. Next question. In the following electric circuit, find the current flowing in the circuit. First we have to find the current flowing in the circuit, that is I we have to find out, okay, and then the potential difference across the 10 resistors. Then we have to find out the potential difference across, that is we have to find out V, okay, potential difference across the 10 ohm resistor. Fine. So let's find out, to find out the current, we know that the formula of current, okay, from the formula P is equals to, from the formula V is equals to IR. How to find out the current? I is equals to V upon R. V for victory, it always at the top, V upon R, okay. So so what is V voltage difference they have given over here is 3 volts. The voltage difference, it is 3 volts, so we will take 3 volts. But to find out the R, we know that these resistors are connected in series. This is 10 ohm and the other one is 20 ohm when they are connected in series. So the equivalent resistance RS will be 10 plus 20, that is 30. Okay, so R is 30. So we are getting 1 upon 10, which is nothing but 0.1 ampere. So 0.1 ampere is current flowing through this circuit. Now we have to find out the potential difference across 10 resistance. So potential difference, that is V I R, and potential difference, current is 0.1 and resistance is 10. So we are getting 1 volt. So this is the answer for this question. Define 1 volt, express it in terms of SI unit of work and charge, calculate, and the next part of the question is calculate the amount of energy consumed in carrying a charge of 1 coulomb through a battery of 3 volt. So let's do the first part of the question, that is define 1 volt. So whenever you get these type of questions, first you write the formula. What is a formula of potential difference? That is V is equals to W upon Q. You can also write delta V is equals to W upon Q. Okay. Now what is the unit of potential difference? That is volt, and unit of work is joule. Then unit of charge is coulomb, and then afterwards just write 1 in front of it because we have to define 1 volt. So now how to define 12 volt? It's become very simple. When 1 joule of work is one joule of work is done to carry a charge of 1 coulomb from infinity to a point. Now I will explain you with the help of a diagram. There is a point over here, that is A, and there is a infinity. Over here there is a charge, right? When you take a charge from infinity, and while doing this you are doing a work of 1 joule. When 1 joule of work is done to take a charge from infinity to point C, and this charge is 1C, right? So when 1 joule of work is done to carry a charge of 1 coulomb from infinity to a point, this is known as 1 volt. Okay, now let's do the second part of the question. Calculate the amount of energy required. So we know that the energy required to move a charge is nothing but the work is done. Whenever you have to move a charge, that means the work is done to move that charge. So we know that from this simple formula, we know that work is equals to V into Q. Okay, voltage upon charge, voltage into coulomb or charge. So voltage given 3 and the charge is 1. So the work done over here is 3 joule. Take question number 4, children. A VI graph for 2 wires A and B. 2 wires A and B are shown in the figure. If both wires are of the same length and the same thickness, which of the two is made up of a material of high resistivity? Give justification for your answer. Now here they have given the graph of V and I. So the graph of V and I, we can find out the resistance. Okay, we have done that with this graph, with the graph V and I, we can find out the resistance. And resistivity is the property which depends upon the nature of the material. Resistivity or the resistance, both resistance and resistivity depends upon the nature of the material, right? So in this case we can see that the resistance of A is more. Why? Because A is making a more slope. The slope of A is more as compared to the slope of B. So in this case, A wire is having more resistance, and we know that resistance is proportional to the resistivity, or the vice versa. Resistivity also proportional to the resistance, right? Because both depends upon the nature of the material, and especially resistivity depends upon the nature of the material, right? So we can say that the resistivity of wire A is more because the resistance of the wire A is more. Now let's check how to find out this. So if I take the resistance of the wire R1, which is rho 1 L upon A, and the resistance of the wire R2, which is rho 2 L upon A, right? And if I find out the ratio of R1 upon R2, I'll find out that L1 upon A and L1 upon A, definitely it will get cancelled. I'll be left with rho 1 upon rho 2. Okay, so we know that by this we can find out that resistance is proportional to the resistivity. Hence, wire A is made up of material of high resistivity. The next question, the figure shown below, 3 cylinders. Now here are 3 cylinders of copper wire. So the material is same. Copper conductors along with their face area, that is the A, and the length L. Discuss in which geometrical shape the resistance will be the highest. So to find out the resistance, we know the formula, that is R is equals to rho L upon A, where L is the length and A is the area of cross section. Let's find out the first figure, resistance of the first figure, that is R1. So this is coming rho L upon A. Fine. So this is the resistance of the first figure. Now in case of the second figure, that is R2, over here rho length is, you can say the length has become double, so 2L we have to take, and the area of cross section has become half, that is A upon 2, right? Now the value of rho L upon A is nothing but R1. So instead of rho L upon A, I will write R1. Okay. Now A upon 2, it will get reciprocate because it is a fraction. So when I solve this, it will get reciprocate. So it will become 2 into 2, 4. Okay. So I am getting over here 4R1. That means the resistance in the second case, it has become 4 times of R1. The resistance in the second case become 4 times more. It's 4 times. Okay. Now let's take the next figure. I will mark it as R3 resistance for this. Again, I'll use the formula rho. The length has become half, so I will write L upon 2. The area has become double, that is 2A, right? So in this case, if I remove rho L upon A and substitute R1 for that, so I'll getting R1, okay, and 1 upon 2 divided by 2, so which is, by solving, I will get R1 1 upon 4. It means the resistance of R3 is 1/4 of R1. The resistance of R3 is 1/4 of R1. So we can see that the highest resistance is given by the figure 2. Okay, here the resistance has become 1/4. 1/4. 6 children. Find the current flowing through the following electric circuit. As you can see the circuit, the current is flowing from the positive term. It is going through the resistance. Okay. And over here, when the current comes, it is dividing into 2 different parts. So this is a junction. Wherever you find junction and current is moving in different direction, the resistors which are connected over here, they are connected in parallel. Okay, so first we will solve these 2 things so that we will get resistors which are finally connected in a series. So we want this. To this we have to first solve this particular connection. So in this case we have seen that 6, first we have to find out 1 upon Rp, and which is nothing but 1 upon 6 plus 1 upon 4. I have directly added over here 1 plus 3, that is 4 ohm, because they are connected in series. So we just have to add these resistors, right? Okay, now if I solve this, I'll be getting 6 into 4, 4 plus 6, that is 10 upon 24. It will go by 2. We will get 2 5 are 10 to 12. Okay, so this is 1 upon Rp, which is 5 upon 12. So Rp will be 12 upon 5, and which is 2.4 ohm, right? And here we got over here 2.4 ohm. Now everything is connected in series. 3.6, I have 3.6, 2.4 ohm and 3 ohm. When you connect it, you will get resultant equivalent resistance. Here the resultant resistance will be 3.6 plus 2.4, which is 6, plus 3 ohm, which is 9 ohm, over here. And now I can find out the current, that is I is equals to V upon R. V for victory, so we always come at the top. Now V is nothing but 4.5 volts as given in the diagram, and resistance we got is 9. Okay, so when I solve 4.5 with 9, I'll get 45 upon 90. 45 upon 90. To remove this decimal sign, I need to multiply with 10. Numerator, if I am multiplying with 10, denominator also I have to multiply with 10. So 45 upon 90, which is nothing but 1 upon 2, which is 0.5 ampere. This is the final answer. Number 7, children. An electric bulb of resistance 200 ohm, that is R, draws a current of 1 ampere, that is I. Calculate the power of the bulb, the potential difference at its end, and the energy in kilowatt hour consumed burning it for 5 hours. 5 hours is the time given for it. The formula, we know that P is equals to I square R. Now, how did I get this formula? P is equals to VR. We know that P is equals to VI, right? But from the Ohm's law, we know that Y is equals to IR. So just substitute this IR over here instead of VIR into I. So I'll be getting I square R. Why I have used this formula? Because according to the question, I have given the current, that is 1 ampere, and the resistance, that is 200 ohm. So if I multiply, I am getting I square into 200, which is nothing but 200 watt. Now this bulb had burned for 5 hours. So 200 into 5, I'll be getting 1000 watt. Because I want answer in kilowatt hour, so I will divide it by 1000, because in 1 kilowatt 1000 watts are there, so I'll be getting answer as 1 kilowatt hour. This is the final answer. Now let's read the next question. Define the term volt. Okay, we have done this. State the relationship between the work, charge, and potential difference for an electric current. There is a relationship between the potential difference of work and charge. We know that potential difference, okay, potential difference, that is V, okay, potential difference, that is V, work and charge, right? So before we come to the conclusion, what is potential difference, work and charge relationship, we will first define the term volt. Volt is nothing but when 1 joule of work is done to carry a charge of 1 coulomb from infinity to a certain point, then the potential at that point is 1 volt. Okay, so from this definition, we can come to the conclusion that V, that is potential difference, is equals to work upon charge. Okay, now next part of the question is we have to calculate the potential difference between the two terminals of battery if 100 joule of work is done. So instead of W, we will put the value, that is 100 joule of work is done, is required to transfer 20 coulomb. So charge is 20 coulomb. We have to find out the potential difference. So 100 divided by 20, that is nothing but 5. And what is the unit of potential difference? That is volt. So 5 volt is the potential difference. Next question. A torch bulb is rated 2.5 volt and 750 milliampere. Calculate its power, its resistance, and the energy consumed by this bulb if this bulb is lighted for 4 hours. The time is given 4 hours, right? So let's find out. So first we have to find out the power. So the power is V into I, because voltage is given, so I'll consider V. I. This formula, that is 2.5, is the voltage, and the current is given in milliampere. So we have to convert milliampere into ampere. So it will be 750 divided by 1000. You can just cross it out, and we can solve this. So here I will just multiply it by 10, okay, and 10 I'm going to write at denominator. So I'll be getting 25 10 into 75 upon 100. If I solve this, I will get 4 over here, and 5 15 5 2 15 upon 8, okay, which is nothing but 1.875 watt. So we have got answer over here, 1.87 watt. Next, we have to find out a resistance. So to find out the resistance, we have the formula V is equals to formula V is equals to IR, and I is equals to V upon R is equals to V upon I. So over here voltage is 2.5, and the current over here is 750 milliampere. So again we can write 750 into 10 to the power minus 3, right? So if I solve this, I'll be getting 3.33 ohm. Okay, now the next part is we have to find out the energy consumed. We know that energy consumed is equals to V into I into T. Okay, what is VI? VI is nothing but power. P is equals to V into I, right? So I can write E is equals to P into T. Okay, now what is power? Oh, given over here, power we got that 1.875. We have calculated power, and the time over here is 4 hours. Okay, power is given in watt, so we have to convert into kilowatt, but we will going to do it at the end. So if I multiply these two values, I am getting 7.5 watt hour. So I need to convert it into kilowatt, so I can write 7.5 into 10 to the power minus 3 kilowatt hour. Okay, 10 to the power minus 3 is nothing but, when you divide 7.5 by 1000, that becomes 10 to the power minus 3 when you write it at numerator. So this is how we are going to solve this sum. Now second question, series arrangement are not used for domestic circuits. Give any 3 reasons. The first reason is electric appliances need current of widely different values to operate properly. So every electrical appliance needs different type of current. So we cannot put it them in a series. Then in series arrangement, if one components get failed, if one equipment or one particular thing gets failed, then the whole circuits gets broken. Then again all electrical appliances work at a constant voltage. But in series circuit, the current is constant throughout the electric circuit, and potential difference across the different components, it's different. So in series arrangement is not suitable for domestic circuits. Next, explain the role of fuse in series with any electrical appliance in an electric circuit. Why should a fuse with a defined rating for an electric circuit not to be replaced by one with a larger rating? That's a very interesting question. So we know that fuse wire, if a current is flowing in a circuit is high, then this fuse wire get melt, so that the devices and the whole circuits remain safe. Okay, now fuse wire is a safety device, so that is why it should always connected with the live wire, and that too in series. Okay, so the safety device connected in series with the live wire of circuit. It has high resistance but it has low melting point. Okay, now it's melt when a sudden urge of large current passes through it and disconnects the entire circuit from the electrical supply. But in case if we use a large rating instead of defined rating, okay, if I using a large rating instead of defined rating, what will happen? It won't able to protect my circuit. It will allow the large amount of current to flow through the circuit, which will definitely going to cause damage. The questions of 5 marker. Question number 1, what is meant by the electric current? What do we mean by electric current? The rate of flow of electric charge is known as electric current. A definition given over here is the amount of charge Q flowing through a particular area of cross section in a unit time T is called electric current. Then name and define its SI unit. Okay, now what is the name of SI unit? We know that current is equals to I is equals to Q upon T. I is equals to Q upon T. So SI unit, there are two SI unit. The first one is ampere, okay, and the second one is what is SI unit of charge? That is coulomb. SI unit of time is second. So the other unit can be coulomb per second. Okay, now we have to define also. We have to define 1 ampere. So 1 ampere can be defined as when 1 coulomb of electric charge flowing through a particular area of cross section of the conductor in 1 second. Okay, so here we can define 1 ampere. Now the second part of the question is what is the direction of conventional current? Okay, if the electrons are flowing from B to A, we know that the conventional current always flow in the opposite direction of the flow of electron, right? If the current is flowing, electrons are flowing from B to A, okay, if the electrons are flowing from B to A, so in that case the flow of the current is always in the opposite direction of flow of electrons. So flow of current will be from A to B. Okay, so we consider that the flow of current is opposite to the direction of flow of electron. So we can say that the flow of current is nothing but the flow of positive charge, right? Then in the next part of the question, calculate the number of electron that flows through any section of the conductor in 1 second. They have given the charge of 1 electron. We know that Q is equals to Ne, right? Q is the charge, okay, which is number of electron into the charge on 1 electron. Q is the total charge, which is number of electron into charge of 1 electron, and we have to find out number of electron. So N will be Q divided by E. Over here Q is 1 coulomb divided by 1.6 into 10 to the power minus 19. Okay, so we are getting 6.25 into 10 to the power 18 electrons. So this is our final answer. Coming to the next question, what is meant by the electrical resistivity of the material? So resistivity is depends upon the nature of the material. So what is resistivity? We have to find out. So mathematically, resistivity of the conducting material is given by rho R resistance into A upon L. Okay, so L we have to write over here. This is what is the resistivity. Derive its SI unit. We have already derived the SI unit of resistivity, that is ohm meter. This is ohm, area is meter into meter divided by L, that is a meter. SI unit of length is meter, so if I cut, I am getting ohm meter. Describe an experiment to study the factors on which the resistance of the conducting wire depends. Okay, so there is an experiment which will show that resistance of the conducting wire depends on what? And the resistivity of the material is defined as the resistance offered by a metallic wire. What is a resistivity? Is a resistance offered by a metallic wire of length of 1 unit length or unit length and a unit area of cross section. Okay, so how will I say define this? If I take a wire, this is my copper wire, right? And if I take a small part of this wire, and the length of this is 1 meter and area of cross section is 1 meter square, right? In this case, if I find out the resistivity of this wire, let's put it into the formula ohm, that is rho is equals to R resistance into my A is 1, my L is 1. If I cut it, I am getting that the resistivity is nothing but equals to the resistance applied by a wire of 1 meter length and area of cross section of 1 meter square. Okay, this is how we can define the resistivity of a material. Okay, now unit also we got it. The experiment I am going to discuss in my next slide. Now let's start the experiment. Here the aim of this experiment is to study the factors on which the resistance of the conducting wire depends. Okay, by the formula of the resistance, R is equals to rho L upon A. From this formula we can make out that the resistance is directly proportional to the length. If I increase the length, the resistance will increase, and the resistance is inversely proportional to the area of a cross section. If I increase the area of a cross section, the resistance will get decreased. Okay, if I increase the area of a cross section, the resistance will get decreased. Other than this, we know that resistance also depends upon the material of the wire. Okay, so let's find out through the experiment. Apparatus required over here is a cell, as you can see, a cell, ammeter, key, and the wires of different length. Here we have taken the first wire, it is a nichrome wire. Okay, and the second wire is also nichrome wire, but the length is double. Okay, nichrome wire with 2L of length. Third is a nichrome wire. Here the area of a cross section is double. Okay, so 2A. And the fourth case, the wire is a copper wire, that is a Cu, copper wire. And the fifth wire we can also take, which is of iron, made up of iron. Right, now we'll start an experiment. So when I switch on the plug, and if I take the nichrome wire first, I will find out the reading in my ammeter, right? I find out the reading of the current in ammeter. Then I will replace the first wire with the second wire, and then second wire with the third, and then third wire with the fourth, and so on. And every time I have to find out the reading of ammeter. Now let's see the observation. When I remove the first wire with the nichrome wire of double of the length, I found that the reading is half. Okay, the current I is half of I1. So in I2 case, the current half is I. It means that when I double the length, the flow of the current is less. It means this wire is giving more resistance. Then when I replace the I2 with I3, there is an increase in the thickness of the wire of the same length, of the same material, and what I found is there is increase in the current. And then in case of I4 and I5, where I have used copper wire and iron wire, I found out different readings of current. The conclusion is different wires drew different amount of current from the same cell. First observation indicates that the resistance of the conductor increases with increase in length, so the resistance is directly proportional to length. Second observation shows that the thicker wire has less resistance, so the resistance is inversely proportional to the area of a cross section. Third observation shows that the resistance of the conductor depends upon the nature of the material. So this is an experiment which shows how the resistance depends upon the nature of the material, the length of the wire, and the cross section of the wire. Question, children. Here you have to derive the expression for the heat produced due to the current I flowing for a time interval t through a resistor R having a potential difference V across its ends. Okay, with which name is this relation known? How much heat will an instrument of 12 watt produce in 1 minute if it is connected to a battery of 12 volt? Now let's see this question in parts. First we have to derive the expression of heat. Okay, we know that heat is produced due to the flow of a current passing in a conductor. Okay, as you can see in this diagram, there is a wire A and B having a resistance R. Okay, and the current I is flowing through this wire having a potential difference. It is connected to a battery which is having a potential difference V, and there is a key over here, right? When a current flows in the conductor, there is always a work done to move the charge from one place to another place. Now, the work done over here is proportional to the voltage across the wire, and it is used to move the charge. So W is equals to Q into V. Okay, now we know that what is Q, what is charge, from the expression I current is equals to Q upon T. We know that charge is nothing but current into time, I into T. So let's substitute the value over here. So when I substitute the value, I will get work is equals to V into I into T, right? So we know that whenever the work is done to carry the current, there is always a heat produced in the wire. Okay, so the current is giving us heat. So this heat, this work can be replaced by H, heat produced in the wire. So H is equals to V into I into T. Now from the Ohm's law, we know that V, voltage is equals to I into R. Okay, V is equals to I into R. So I'll substitute the value of V over here, which is I into R and I T. Now if I simplify this, I'll be getting I square R into T. So heat is equals to, that is H is equals to I square R into T. So this is the expression of heat produced in the wire. This expression shows that heat is directly proportional to the square of the current passing through the wire. More the current passing through the wire, more the heat is going to produce. More the resistance of the wire, more the heat is going to be produced. And more the time the current is flowing through the wire, more the heat is going to produce. So we got the expression that heat is proportional to square of the current, heat is proportional to the resistance of the wire, heat is proportional to the time the current is flowing through the wire. So this expression is known as Joule's law of heating. And heat produced in 1 minute, we know that H is equals to, we can simplify that Pi, V into I can be written as P into T, and power is given 12 and time is given 2 minutes, 1 minute. So 1 minute has 60 seconds. So I'll be getting 720 joules. So heat over here is 720 joules. Let's take the next question. So let's do the sum. Over here, the circuit is shown which has three identical bulbs B1, B2 and B3. As you can see in this picture, B1, B2 and B3 bulbs are here. B1, B2 and B3 bulbs, right? And you can see the ammeters are arranged along with the bulbs. They are connected in parallel, as we can see over here, and the battery of volt 4.5. Okay, so it is also connected. Now what will happen to the glow of the other two bulbs if the bulb B3 gets fused? If this bulb B3 gets fused, what will happen? Because these bulbs are connected in parallel, there won't be any changes in the B1 and B2 bulb. Okay, so glow of the B1 and B2 will remain same even if the B3 get fused. Okay, because they are connected in parallel. If the wattage of each bulb is 1.5 watt, how much reading will the ammeter A shows when all the three bulbs glow simultaneously? So we have to find out the reading of ammeter. For that, we have to use the formula, that is P is equals to VI. Power is given in watt, and V is also given over here, and I we have to find out. So I is equals to P upon V. So first we will find out the I of the first bulb. Okay, so I1, P upon V. So 1.5 divided by 4.5, as you can see over here, power is 1.5 divided by 4.5, point will get cancelled. This will become 1 upon 3 ampere, right? And here again for I2 we will be getting same thing. For I3 also we will be getting same reading. So 1 upon 3 A will be the reading for all the three bulbs and all the three ammeters, right? So total current will be, what will be the total current? As we know that the current is different in case of the parallel connection, voltage remains constant, right? So we have to find out the current across each bulb. That we have found out, and that is coming 1 upon 3. So we'll just add all the current, 1 upon 3 plus 1 upon 3 plus 1 upon 3. The will be LCM is 3, and 1 plus 1 plus 1, that is 3 upon 3, and 3 upon 3, that is 1 ampere. So current flowing through all the three bulbs, or total current flowing through the circuit, is 1 ampere. Now what is the last question? We have to find out the total resistance of the circuit. To find out the total resistance of the circuit, so we know that P is equals to V square R. So using this formula we can find out R. So R will be V square upon P, right? So voltage is 4.5, so 4.5 whole square upon P, watt is 1.5, and what the answer we got is 13.5 ohm resistance, right? Because they all are connected parallelly, so what we have to do is we have to add all the resistance, that is 1 upon R1, 1 upon R2 and 1 upon R3. By doing so we are getting 13.5 upon 3, which is 4.5. So 4.5 is the equivalent resistance in the circuit. The next question, that is 7th question, children. Though a same current flows through the electric line wires and the filament of a bulb, yet only the filament glows. Why? Okay, so the same current is flowing through the electric line wires. We know that electric line wires, they are made up of copper. They are made up of copper, or they are made up of aluminum. The copper and aluminum, they have very low resistance. They are extremely low resistance. That is why they won't glow. But the filament bulb glow. Why the filament bulb glow? Because filament bulb is made up of tungsten, and tungsten gives a high resistance to the heat or the flow of the current, and because of that it gets heats up, and it produces a glow. Okay, the filament of bulb glow because it becomes red hot due to the large amount of heat produced by it offer into it, and in the bulb there is a nitrogen mixed with the argon which gets ionized and then it glows. Okay, next question, the temperature of the filament of the bulb is 2700 degrees Celsius when it glows. Why does it not get burned up at such a high temperature? See, the tungsten wire, it can melt at about 3380 degrees Celsius. Oh, because of that 2780 degrees Celsius doesn't make any changes in tungsten wire, so it doesn't get burned because it has a high melting point, first of all. Second is they have a high resistivity. It has a very high resistivity. Let's take the next part of the question. Let's do the next part of the same question. The filament of an electric lamp which draws a current of 0.25 ampere, that is I current, used for 4-hour time T. So 4 hours they have given, so you have to convert 4 hours into second, that means 4 into 60 into 60, and calculate the amount of charge flowing through it. We know that charge from the formula I is equals to Q upon T. So charge is equals to I into T, right? So current over here is 0.25 into 4 into 60 into 60. So we are getting 3600 coulomb because 0.25 into 4 is nothing but 1 into 60 into 60, that is 3600 coulomb. Next question, an electric iron is rated 2 kilowatt at 220 volt. Calculate the capacity of the fuse that should be used for the electric iron. So what formula we are going to use over here is P is equals to V into I. Okay, so because we have to find the amount of current that is flowing through this fuse. We know that the fuses used for domestic purposes are rated as 1 ampere, 2 ampere, 3 ampere, 5 ampere and 10 ampere. So we have to find out the appropriate fuse used for this. So to find out this, we know that P is equals to 2000. We have to convert kilowatt into watt, that is 2000 watt, and voltage is 220 volt, and I. So I is equals to 2000 divided by 220. So 0 will go off and this will go by 2. I'll be getting 100 upon 11, and which is nothing but 9.09 ampere. So over here I can use the fuse of a capacity 10 ampere. And this is all about today's session, children. Please practice all the sums. Thank you so much.